Welcome everyone to our DYNAmore webinar. And today my colleague Rasmus Schützer from DYNAmore Nordic will give us a talk about how to use a Python toolbox to have an advanced possibilities for DYNA or LS-DYNA post-processing. Yeah, when you do simulations, maybe you want to extract data, you want to do something with the data, and there is a Python toolbox available, and Rasmus will talk a little bit what you can do with it and so on. With that being said, Rasmus, are you ready? You can share your screen then.
Yes, I will take over the screen, and I hope that everyone can hear me.
Yeah, I can hear you. Okay, yeah, switching the screen. Okay. Yeah, I can see your screen. Perfect.
Yes, so I hope that everyone can see the screen, and then I think we're gonna start. So, hello everyone. My name is Rasmus Schützer, and I'm with the DYNAmore Nordic guys up in Sweden. So we're part of the DYNAmore group. So I'm gonna give you a webinar on the recent developments in the DYNAmore Nordic Python toolbox, which is to help visualize and build tools specifically for LS-DYNA. And as Max said, that you feel free to post questions in the chat, and we'll take that at the very end. So, a bit of a background on what we're going to see today. So today's topic, first we're going to go into some background of the toolbox, and we're going to go into some specifics for the DYNAmore toolbox itself. We're going to talk a little bit about the binout format in LS-DYNA. I'm sure that most of you know it as LS-DYNA users. It's a binary format. It can be read by post-processors such as LS-prepost. And then I'm going to switch over to give you a hands-on experience where I will show some live demo. I will walk you through how you can use the library to access data, how I'll give you a bit of an insight in how I like to work with the tools when I develop post-processing scripts. And I'm going to do with that, I'm going to briefly introduce some other helpful and commonly used libraries and data structures within Python itself that I've based the toolbox a bit on, and to help you with plotting and such. And then I'm going to show a example with an LS-DYNA model of the kind of post-processing you can do with the Python toolbox, and also walk you through the script to some extent to show you to get you started, so to say, so that you can get inspired to do your own post-processing. And also at the very end, explain the steps needed to get access to said tools. So, why develop tools for LS-DYNA using Python? As an engineer, I'm sure a lot of you can relate to that. Sometimes there is some repetitive tasks that you have to do. This can be small things such as plotting energies to determine the model's numerical soundness, or plot the same figure over and over for a bunch of different load cases, for example. And what Python can help here is, of course, automate these repetitive tasks, and also provide some consistency so that you always get the same looking graphs and figures, and they are calculated in exactly the same way, so you're not missing any steps. This not only helps you with making pretty plots, it also helps you to speed up the process, because I'm sure a lot of you have also forgotten to change the labels on the axis, for example, or change the scaling, have consistent colorings and such. So it will improve that also. And also for documentation wise, it's really nice to have a script that tells you, okay, this model or this result was post-processed just like this, and you can follow the code and you can really see, did I do something wrong, or how is this generated? So it's a nice documentation also. And of course, it opens up the possibility to do some more advanced post-processing things, which, for example, require a very high sampling rate that you can't export in the D3 plot file because they will get very large. And also you have to process a lot of data, and that can take time. And if you can do that using scripts instead, that is, of course, very nice. And also, there's no licensing cost related to the Python programming language. So that is, of course, nice that you can use it as is, and you can scale it to other people within your company and such. There's no licenses that you have to think about that. And of course, the access to other Python tools and libraries that you might find useful. I mean, there's so many Python libraries. For now, there's coming up a lot of machine learning, for example, if you're into that. There's a lot of different plotting tools, doing numerical calculations and such, optimization, curve fitting, and all of these good stuff that's out there, and that you can easily connect to your post-processing or use in your post-processing. So, with that said, a short introduction to the DYNAmore Nordic Python toolbox itself. And it has grown from some previous work and projects where I found that we needed to be able to get consistent plots, and it will really help with speed and such, building sort of black boxes to post-process a lot of data. And it's not meant to be, a complete and full post-processing box, but rather it could provide a good starting point and get you to that you can read the code, and if you're finding that something is missing, you can just add it, and hopefully I have written the code so that you can see what I have done when I've added functions or read the data, that you can probably add it with the help of that, so that you can read the data that you're interested in. And with that said, I hopefully also that there is an intuitive data structure to work with. Hopefully it should be quite easy to use it. And of course, most important, what you want to do is you want to make nice plots, and you want to show something in your model, and you don't want to develop a whole post-processing box from scratch. You want to write quite low number of code lines, and to get what you want to express. So, about the binout file, or the binout format a bit. So when you want to export data for multiple nodes or elements in LS-DYNA, you typically define this using star set and the database history of that set. So say you want to export a few hundred nodes, for example, the data, you typically create a set of that data, of those nodes, and then you export them using the database history. And the same can be done with, for example, elements. You want to have some high resolution in one area, for example, and then you want to export it based on the element set. But the problem with the binout is that almost all data regarding the model is lost, all the metadata. So the nodes, for example, or elements, they do not know to which part they belong. They don't know to which set they belong, what are the material, and such. even what is the title of the part there in, if you go it one step further. And this can of course make automation problematic. Not only do they not know where they are, so you can't filter and do some special things, for example, in one area, but all get exported into the same structure. And what can be typically done is, for example, resolving ranges of node IDs, for example, or element IDs for a specific task. But this, of course, hinders the modularity a bit. You have to kind of hard code it in to the post-processing, and you probably can't use it for the next simulation, or if someone else is building the model, you have to tell them exactly how you're going to build it and such. So it's, yeah, it's not optimal, so to say. And with that, some new functions has been added within the toolbox to read certain model data from the keyword file, and so that you can use this data to filter and to categorize your data, so you can do the complex post-processing that you want to. So there's functions to filter node.data by the set ID, for example, of the set node list card. So say you defining a number of node sets, and you want to do some specific calculation on the nodes in one of the node sets, you can easily filter it out by the set ID. And this functionality is also for the allout, for example, for set solid cards. So you can do one local calculation in an area. And this, of course, opens up more possibility to find, for example, local max and mins of some variable rather than on the whole model itself. And you can also, for example, find things between two node sets or such like that. So it really opens up the door to more advanced post-processing. And also another concept is the chaining of keyword cards. So here we have the element card that I'm sure a lot of you are familiar with. It's the element solid. So we have the element ID. This is what's getting outputted in the lout in the binout file. And that's it. But you can, of course, go into the element card and read it. So you can see which element ID corresponds to which PID ID. So that's nice. And what you can do then, where is the information of the PID of the part ID? That's on the part card, of course. So then you can look in the part cards. And for example, you can go from the part ID to the heading, for example, that is the title of the part. And if you see the chain here, you can go from the element ID to the part, to the title, for example, or you can go to some other part of the keyword. So now that opens up the possibility to, for example, find which title of the part is this element part of, to help you with making some nice plots. So here is one example that I will go through with you soon also. It's part of the script, where I have done part comparison. So I have filtered and categorized a lot of element IDs, and I have then found which part, the maximum value for each part, so to say, and plotted it. So we keep the element ID here, for example, of the max per part, and then we have the PID part ID, and we even got the title of that part. So that's really nice to be able to make such plots. So you can quite easily, okay, so here, which part is it that gets most deformed? I mean, yeah, that's a bracket. We get the value also. And so now that's part one, then we know where to look. And if you really want to look more detailed where it is happening, you can look at the element itself in the digit plot, for example, so you know which area is affected. So that's one example of the kind of figures and tools you can build. So with that said, I think we're gonna move over to some live demo. So I'm gonna move over a window of the Python IDE called Spider, which I usually use to write code and develop code. And with that, I'm also gonna show you just quick a model. Okay, so here we have a model of just a bracket with some bolts and such. So I've exported some binout data for this one, just so that we have something to read. So what I'm doing here firstly, I'm doing some importing of some libraries that I'm usually using. So the first one here is the matplotlib, and that is pretty much a plotting library that's the most used, I think, in Python. So that's going to help us making plots. And the NumPy, which is kind of has a lot of tools for doing matrix operation and vector operation and such. And also gonna import Pandas, which is used for building the data structure that I've been using for the tools. And then the library that's been using to read the binout itself, that is from the library called QD, which is on GitHub, so you can download it using pip, for example. And then I'm gonna import binout, which is using to read the binout data, and I'm also gonna import keyfile, which gets us to read the keyword file as text and sort them into based on the keyword itself, so I can loop through them and such. And then from the DYNAmore Nordic Python tools, first I'm gonna import the function getNodeCoordinates, and as the name says, this is loading the nodal data. So this will pretty much load the nodeout data. And also just so that you can follow what everything is. So here is the file itself that I'm writing in. Down to the right here, it is a console. So this is a Python program running. So I can do, for example, 1 + 1. I mean, that's 2, a equals to 1, and such. And then we have the variable explorer up here, where you can go and look into which variable is loaded into the session, we'll say. So you can open it up and look what's inside, we'll say. You can easily find the values or what's in it, so to say. So, and also, so I'm standing in a folder that has the binout data of that bracket model I showed. So to load the data, we're gonna write like this, binout. We're gonna declare a variable called binout, which is equals to using the binout function that I loaded earlier, like this. And then I'm gonna load a string, which is binout.star. And the star is gonna tell it to load all of the binout files within the folder. There's a lot of binout to keep track on, but hopefully you can see the differences. And then I'm gonna run this script. And you can see that it's loading an object from the QD module with some possibility to read binout data. So now I'm interested in reading the nodes, node data. So I'm gonna declare a variable which is called nodes. And then I'm gonna use the function which I loaded here from the Python DYNAmore Nordic Python toolbox, which is get node coordinates. And into that, I'm gonna put the binout that I've declared over here and run it. And so it will look into the binout file, and it will read the nodal data, and it will give you a Pandas data frame, which is a library which is called Pandas, which is very good to structure data in a table, so to say. So I'm gonna open up this data frame, and you can see, okay, so here is the entities that are loaded. Okay, X, so that is the X coordinate, for example, and we have the which node ID, so that is here, and it's also been structured in time. So each of this is one element, for example, and one entity. So this column is for the X coordinate of the node 206, and then it's in time. So, and if you want to filter that out, for example, you can just call it like this. You call the nodes, and I'm interested in the X coordinates, for example. So then we have exported the X coordinate, for example. So you see, we have lost one row here, and so now we only have the nodes and their value in the X coordinate and in time. So see what I did? I used this the terminal to write something and check if this works well, and then I'm gonna move that over here. So for example, I'm gonna call this X coords, for example. And like this, and then I can run it and declare the variable here. So it's quite easy to find what's in the data structure that's being given by the toolbox itself. So you can go up here and just scroll through it, and you can see, okay, so we have X data, for example. Now I have a lot of nodes. Maybe when you're gonna explore the data sets, maybe just load a few nodes, so to say. But when we go further to the right, we're gonna see, for example, Y displacement also. So you can also just do it like this. You can see if there's an X, there should probably be an Y. Yes, there's also a Y and a Z. And maybe there is a XY displacement. No. like this. So then we also have, so for example, the plane displacement in XY direction that's been calculated. And I mean, you can go into the source code when you get the toolbox to just look what is calculated and what is imported also. Okay, but so this is the command to just load this whole thing. And then I'm gonna now import another one, which is the get section force. So I'm gonna look at the forces in the section of the model. So I'm doing a pretensioning phase, for example. And this is done the same way, using calling it using the binout. So I'm declaring the section force in the variable secfork. So here we have fewer values. So here we can see, so here we have the X force, we have the Y force, Z force, and we also have the resultant force for the cross section. So that is the data that's loaded. And here I only have one cross section, and that is the number 1. Okay, so that is just a quick introduction to using the tools to read binary data. And there is a lot of more functions like this. Actually, we can switch over here to the toolbox itself. So we have a function for reading SPC force. We get the GL-stat, the statistics for the global energies and such, matsum, BND out, contact data, section forces, stress and strains for solids and shells, for example. So you can go into here and find if there's something that you're looking for, so to say. And now we're gonna move over to the second part, which is more about reading DYNA data, or the model data, so to say. So I'm gonna declare a new variable here, which is kf for the keyframe, the key file. And then I'm gonna use this function which I've imported here, which is called keyfile, and I'm gonna read the bracket.k, which is the file, the keyword file that I've been using for this example. And I'm gonna tell it to read with keywords equals true. So, okay.
Big F.
Thank you, of course. Like this. Now we're calling the right function. So we're done reading the bracket.k file. And then we can look into that a bit. So, for example, we can use the functions within it. So kf.keys to find what are the keys that's part of this the model. So these are the keywords that you've probably seen a lot. I mean, there's controls, there's database, nodes, parts, element solids, and such. So say that we, for example, I'm going to save this as a temporary variable so that I can look at it in a list. I can scroll through it. And then say that I want to load, for example, part. So then I go like this, and I call it using star part. What is this? This returns a list. So we can see that we have a number of parts, 1, 2, 3, 4, 5 in total, which I know that I have 5 parts in the model. So it returned the list. So I'm gonna print out the null element, or the first part, like this. So here we have the keyword for part with PID ID 1, that is the bracket. We have the section ID, material ID, and such. So then we have the information for the part itself. So this can be, of course, then be used to read the data for the model. And I have done a few functions for doing that. Get you started. But first, I'd like to talk some things about dictionaries in Python to introduce that concept. So that is a structure where you have a key that points to some other object within the dictionary. So it looks like this. I'm going to declare a simple dictionary with a key. So this is a string that says key. I'm just going to point that to some kind of target. So now if we call the dictionary with the argument, or I'll look at it with the key, then it will return what it's pointing to. So this is the key which points to this object, and this object could be a list, or it could be a data frame or something like that, for example. So it's quite nice to have. And we can also extend this dictionary like this. Say we want to add another thing. So key number 2, that is going to point to target 2. And so then we can look, for example, up here, that we have the key object here and what is pointing to. And so that it's been added the second key. And as I said, this could also be, for example, a list. So I'm gonna do that real quick. So for example, a list with a number of items. Let's make it 3 items. So item 1, item 2, and then the third item. So then we can, if we then call it by key 3, then we can get a list of items. So this could, for example, be the node IDs, which is part of a set ID, for example, or such things. But it's good to be able to look through the dictionary to find what is part of it. And so you can do that either with the variable explorer here, for example, in Spider, or you can also just print it. I think. Like that. So then you get a list of the keys that are part of the dictionary. So with that, let's import another function here, and that is what I'm calling get dictionary of set node list. It's quite a long one. Let's see if I yes. That is another function that you can see here. So this one. So then I'm going to use this function to get a dictionary with set ID to nodes. And I'm going to put in the kf, so that is the objects of the keyword file. I'm just going to run that. So we see now that we have a new dictionary. So here we have the set IDs in the key. So we have 1, 200, 200, 100, 200, 201, and 1000 with the corresponding number of nodes that I've defined in the model. So that's how you can use it. And let's, for example, call it real quick, and you can see you exported you're getting a list of each node ID. So what you can do with this then is if you look at the nodes that we have loaded from the binout file, for example, you see, okay, these are entities is X. And so if you want to call this column, for example, you go like this. Okay, so that is nice. But what if you want to call a bunch of these data, for example? So now first I'm going to show you, for example, that you can call them using a list. Like this, then we'll get all X and Y coordinates. But I'm gonna first flip it around using a Panda, using the built-in functions in Panda. And it looks like this. So we're taking the X, Y, and Z data, and we're gonna swap the levels. So we're gonna switch it so that the node ID is on top and the entity ID is on the bottom. And then we're gonna sort it by the nodes. like this. So now I've flipped it, so we can look at it real quick. We see that now we have the node IDs on top and we have the entity at the bottom in a new variable called nodes flipped. So let's call this using for example, the set ID of 100. So then you've filtered out all nodes with X, Y, and Z data within the set 100. And this concept applies also for the element ID and such, for example. So now I'm going to move over to another part, which is the pre-made Python script that I've done for this bracket. And I'm going to show you the model a bit first. So what we have here is a bracket that is being preloaded, and I have defined a number of sets. So, for example, this set is on the plate to get the coordinates from that area. And then I've made yet some for this rigid puller that I'm going to use to load this structure. And this is going to spin. And I'm going to find what is the minimum distance between those parts while this is spinning and loading away from the plate. I'm going to use another tool that I've done in the toolbox for that. And also to I'm gonna use another tool to measure the distance, the length of this of the hole here, how it changes if it gets longer, shorter, and such. So I've coated that with node sets, and I've taken the start node here, and it's gonna give me the length here of this node, of the length of inside here. So I'm also just gonna load some Dieter plots to show you what's happening. Okay, so this is the process. You can see this part is spinning, and then it's pulled up. So I want to find what is the shortest distance between this part and the set down here, for example, or well, between those node sets. And also this hole is going to get some deformation, so I want to calculate the length change here. And I have also defined a set of elements that I'm going to be using for calculating some strains. So it's all of these elements that you can see here. So quite a lot of them. So I want to find per part the maximum principal strain. So at the beginning here, where I'm loading in the keywords, and quite a lot of tools from the toolbox just to highlight. And then I'm using them to declare the dictionaries and such to get the variables. I'm loading in the nodes, the strains. And then here I'm using a function which calls find the shortest way node set. this takes the starting node, and then it takes a list of the nodes. So here I'm using the set ID 1000 that I'm gonna put into the function, and I'm gonna send in the coordinate data by the nodes that I've read from the binout. And this is gonna give me the path. So it's gonna give me a list of the nodes in order from the starting node. It's also gonna give me a list with node path parse. So that is what's gonna have to be calculated, the distance between. So it's the first and second, the second and the third and the fourth, and so on. And it's also gonna return the filtered nodes that I've done the calculations on, and it's also gonna export some length and displacement figures to the actual calculation itself. So that is one function, and another one is the find distance between node sets, which takes the nodes, that is the coordinate data. It takes one list of the set ID from one node set, and the other one, and it's going to calculate the maximum and minimum distance between those node sets in each and every part of the binout in time, and it's going to plot that down here. And down here I've done some I've used the indexes of to get a list of elements, and I've used the dictionary element to part ID to build up a structure where I can filter. So I couple each element ID to a part ID so that I can reduce them by the part, and then do some nice plotting of set part with, for example, element ID, part ID, title, and such. And also I'm using reading the title of the part there in also. But this code will be bundled with the toolbox, so you can go back and look at it yourself and use it once you get hold of the toolbox. So I mean, it's not a lot of code, actually. Most of it is plotting. So all of this is, for example, plotting. All of this is plotting. And down here, it's pretty much plotting. So it's almost to include as many functions as there is lines of code to do the things. So I'm going to run this. It takes a little bit more time than the usual ones or the previous ones, of course. But then again, it's quite quick also. Let's see. And just to give you some perspective, this is about a gigabyte worth of binout data also that is have to read and do the calculations and so on. So then we get exported these nice plots. So this, for example, is the length change of the hole itself. I mean, it's not a lot, but if that is what you're interested in, the change along some arbitrary set of nodes, then that could be really useful. And also we get the part comparison plot that I've shown earlier with the element ID, the part ID, which title it is, and such, and get one curve for each of them. And we can, for example, add a requirement so that we can see, okay, which part is failing this requirement that we're setting on this simulation, for example. So here, it would be only the bracket all other ones pass it. And also here, so this is the minimum distance between those two sets. So remember, they are spinning and moving from each other, and still a nice curve, and also the maximum distance between those node sets. And of course, you can use these functions to do a lot of local things, for example, and do them in parallel, for example. So now I'm gonna move over to the part of getting access to the tools. And as for now, the tools will only be distributed to the DYNAmore customers, not only the DYNAmore Nordic, but of course the DYNAmore, which are part of the DYNAmore concern. And you will have to sign a license agreement. This is done digitally. It's so that we can know who is using the toolbox, so that we can give some support and such and help you. And after we have received a signed license agreement, you will obtain instruction on how to download the tools. And that is complete with, for example, recording from my previous webinar, this webinar, example models, and the code that you've been seeing today, for example, and of course the toolbox itself. And if you already have a signed license, some of you might already have it from my last webinar, for example, you can just contact us and we will get you a new link to download the latest version of the toolbox. There have been quite a lot of changes. And finally, so to start the process of getting access to the tools, you send an email to support@dynamore.se, and we will help you as best we can. And with that, I thank you for joining this webinar, and we're gonna move on to some questions and such.
Thank you, everyone. Thanks, Rasmus, for the talk, and see you next time.
Yes, thank you for your attention, everyone.
Yeah, bye-bye.